In this video, we'll look at Karnaugh maps and their ability to represent sample spaces. So a Karnaugh map or probability table is a visual and algebraic representation of a sample space. So one is shown over to the right hand side of the screen. In the map, the probabilities of A and A complement, so remember that A dash is A complement, are placed in the middle columns, and we have the probabilities of B and B complement placed in the middle rows. So the names of these events A and B could change, and you could also put A in the rows and B in the columns. It doesn't really matter, but that's how we set up our Karnaugh map. The four cells in the center, which I'll highlight or outline in red, these represent the intersections of different sets, and we'll explore that a little bit more in a moment. The sum of each row and column gives the probability of that event. So adding up these two things will give the probability of A, and then adding up these two cells would give the probability of A complement. And the same thing holds if you go across the rows of B and B complement. We also need to remember that the probability of A plus the probability of the complement of A equals 1. And likewise, the probability of B plus the probability of the complement of B equals 1. That means if we sum up here or sum down here, we'll always get to 1. So that's a useful property of the table that we can use to solve more complex problems. Finally, just to note that Karnaugh maps are limited to representing two events. So if you want to represent more than two events, we can use Venn diagrams and tree diagrams as an alternative. Next, we're going to explore what the intersections mean for the Karnaugh map. So the first cell that's highlighted there in blue is the probability of A intersecting B. And on a Venn diagram, that's the overlap between the circles of A and B. The next cell is the probability of A intersecting complement of B. So that is everything in A that's not in B. So that's shaded in on the Venn diagram shown. The next cell in purple is the probability of A complement intersecting B, which is essentially everything in B that's not in A. And again, that region of the Venn diagram is shaded in purple as well. Finally, the probability of the complement of A intersecting the complement of B are all the elements in the sample space that are not in the circles of A or B, so it's shaded in that Venn diagram. Lastly, we just remember that the 1 comes from the fact that all the probabilities of all four of these cells include the entire sample space, or the entire Venn diagram, so they all sum up to be 1. So next we're going to consider the sample space where the probability of A is 0.4, the probability of B is 0.75, and the probability of A intersect B is 0.25. So part A asks us to represent this data using a Karnaugh map. So the probability of A is 0.4, so that will go at the bottom of the column which represents A. Next, we know the probability of B is 0.75, so that will go at the end of the row that represents event B. The last piece of information we have is the probability of A intersect B is 0.25, so that goes in the cell that represents the intersection between A and B. Now, in order to solve all our problems for this question, we need to remember that all of this sums up to 1. So because it sums up to 1, we know 4 plus 0.6 equals 1, therefore the complement of A is 0.6. We know that 0.75 plus 0.25 is going to add up to 1, so the complement of B is 0.25. Now, because of the way the Karnaugh map is set out, we know that the probability of A intersect B plus the probability of A intersect not B is equal to the probability of A. So we know that this column here must add up to be 0.4, meaning this cell is 0.15. The same thing happens adding the rows. So we know 0.25 plus something must equal 0.75, so that must be 0.5. And then we know 0.5 plus something equals 0.6, which is 0.1. We can also check that that works by going 0.15 plus 0.1 is equal to 0.25. So we're all okay. So for part B, we're asked to find the probability of A intersect the complement of B. So in our Karnaugh map, A intersect B is right here. So we can just read the answer straight off our Karnaugh map. Therefore, the answer to this is 0.15. Part C asks us to find the probability of A complement intersecting B complement. So in our Karnaugh map, that's this cell here. So once again, we can read it straight off the map and know that that probability is equal to 0.1. Now the next question asks us to find the probability of A union with B. And this is a little bit more tricky because none of the cells here represent that information specifically. But what we can do is we can spot parts of this Karnaugh map that can help us. So we know that all of this adds up to being 1. So if we were to take the 1 and then subtract away the probability of everything that's not in A intersecting everything that's not in B, we would find the probability of A union B. So what we've essentially done is we've looked at a Venn diagram where you would have A and B, and then we have looked at all of it that is not in A and B. So all of this here is represented by this green number here is everything that's not in A and B. If we take that away from 1, we find A union B. A union B is all of this, which is what we're after. Therefore, we have 1 minus 0.1, because that's the probability of A complement intersecting B complement, which equals 0.9. So after this video, you should be able to know when to select a Karnaugh map to represent a sample space. You should be able to use a Karnaugh map to visually represent sample spaces and events. You should be able to use the Karnaugh map to determine the probability of events occurring. You should understand the similarity between Karnaugh maps and Venn diagrams. And finally, you should understand the limitations of Karnaugh maps and know alternatives to overcome these.